Alright, welcome everyone. Combinatorics of posets, 5 lectures. It's so nice to see so many youngsters, people just before or just after PhD. It's nice to have also some colleagues here. What this will be all about? So, Dilworth theorem is from 1950, right? The notion of poset dimension, I think, was introduced in 1941. But I think it's fair to say that that the research and a bulk of papers gradually started to grow around 70s, right? I think what I want to do here within this course is, well, first of all, show you some nice combinatorics, some visually pleasing arguments. But I also want to share my enthusiasm to this topic, and I will try to convince you that it's maybe the right time to attack that we kind of have an angle for some long-standing open problems because of last decade of research, because of some connections discovered specifically with sparsity business that will show up later in this course. That's my agenda here. So, nice to have you here, and let's go into the topic. I should say that the dynamic at the beginning will be slightly different than at the previous lecture and course, because I feel I shouldn't assume so much about poset theory as we all know about graph theory. But I hope we will be done with it quite quickly. So let's do it. Yes. Okay, so that's the main character, right? It's a partially ordered set, it's a pair. You have a ground set. Usually in our business it's finite. I mean, the topology of the building is difficult, but we are on the computer science side of the building. If you, please go on the other way. If you have problem with finite structures, a binary relation that we study here is reflexive, antisymmetric, and transitive. Yeah. And that constitutes a poset. So that would be an example, except it's unreadable. So this is how we visualize it. This is something we eventually call a diagram. In order to capture this notion, let's take two elements of a poset, and then they can be comparable, which means that one is less than the other, or the other is less than the one. Or they can be incomparable otherwise, right? Then there is also a little bit more subtle relation, which we call a cover relation. So one element, x, is less than the other, and it's in a cover relation if there is no element in between. Then it's a cover relation. And then based on these relations, you can draw graphs, yeah? So you can draw a comparability graph, which usually is a big mess, because as long as you have a long chain, it gives you a click in the comparability graph. So if we want to see the structure and say that some drawing is nice, we usually just draw the cover edges, claiming that the other you can induce by transitivity. Yes, and the diagram itself is a very special drawing of the cover graph. This is such a drawing where, when you have two elements in the cover relation, so the one which is less in the poset relation is actually drawn below with respect to the vertical coordinate. Yes? And then the edge itself is drawn in a y monotone, so maybe I should say vertically monotone fashion from x to y. Yeah? And that is a diagram. Yeah? Yes, so we're done with this. And now, yes?
Can you get any DAG as a cover graph? Or just to try to get some intuition?
Well, okay, so first of all, cover graph is an undirected graph, but there is an obvious orientation of it, and this is what you are thinking about. Second, as long as you don't have edges coming from transitivity, that's it, yeah? Because the cover graph itself is exactly this smallest diagram that generates the its transitive closure, right? So yes, yes.
Okay.
In short, the answer should be yes. Yeah. Now, when we have a picture in front of us, we can visualize what is a chain. It's just a set of elements that are pairwise comparable, and the height of a poset is just the size of the largest chain. Yeah. So in this example, we have a chain of size 5, and I think there is nothing larger, so the height is 5. The width comes from antichains. An antichain is a set of pairwise incomparable elements. So here you see an antichain of size 3 in the poset. There is an antichain of size 4. There is nothing larger, so the width of this poset is 4. Now, there is an observation which is usually called the dual of the Dilworth theorem, or the anti-Dilworth theorem. This is an easy observation that when you have a height h poset, you can partition its elements into h antichains. And that's fairly easy, right? Because all you have to do is you have to take the minimal elements, take them out. Please note that when you have two minimal elements, they are incomparable. So the set of all minimal elements of the poset is an antichain. And you iteratively take out these minimal elements, getting antichains in your partition. So that's a partition, yeah. Now you can now the thing to observe is that you have at most h, or you have actually exactly h antichains. Where
taking out minimal elements iteratively and simultaneously, they would be different in this case.
Iteratively or simultaneously? Well, maybe I will explain myself what I think, what I mean. Yes, and you will repeat your question. So you have a poset. I don't want to draw specifics, but there are the minimal elements. Yeah, and what I claim here is that you should take them out, and that's your first antichain, A1. Now you consider the remaining poset. Yes, which is here. Yes, okay. And then again, take its minimal elements, yeah? Take them out, yeah? So that maybe they are green, yeah? Take them out. That's A2. And continue. That's a partition into antichains. When height is h, we have exactly h antichains. Because when you look at the chain itself, the elements must be in different antichains. Because an intersection of a chain and an antichain has size at most 1. Yes? Second, you have h antichains. Well, that I argued. Second, there are at most 8 antichains here. Why is it so? Well, you have to think what happens if you say that you're using A10. If A10 is non-empty, what does it mean? It means that there is a chain down, yeah, on 10 elements. So indeed, the height is exactly the minimum size of an antichain partition of our poset, yeah? And that's the dual to the Dilworth theorem. There is a Dilworth theorem, which is a little bit more difficult to prove. Nothing mind-blowing. We're not going to do it today. This is one, actually my bet is that this is one thing you could actually have seen during some combinatorics course. The statement is that when you have width W poset, its elements can be partitioned into W chains. And again, obviously, this is best possible because the antichain witnessing the width must be distributed into different chains, right? The fact that you can actually do it so optimally takes an argument. So the argument that people used to give is, I think it's not the original argument of Dilworth. Yes, it comes from some paper from 90s. The argument for Dilworth theorem that we used to see these days.
Oh, Paris, 1960, 63.
Okay. So slightly after Dilworth. Anyway, we are heading for poset dimension a critical thing here is a linear extension. I think when we discuss posets, partially ordered set, there is a premise that there is something behind, yeah? Partial, we have something partial, maybe there is something complete behind it, yes? And that's the okay, if we buy it, then, okay, what is behind? Maybe there is some total order that we don't see. Maybe we just draw what we see, it's a partial order, but there is something behind. So this possible thing behind is a linear extension of a poset. So what is it? It's an order, it's a linear order on the same ground set as our poset, and such that it respects the poset, which means that whenever you have two things comparable, well, one x is less than y in the poset, it must be x less than y in the linear extension. Yes? That's the notion of a linear extension. So here you have an example, a very simple 4-element poset, and you have all 5 of its linear extensions. Now, yeah, I mean 4 elements, so possible number of permutations, 24, right? Not all of them are legal, yes? Because you cannot put D below A in a linear extension, correct? Yes. So a thing to say here, which I think we could miss, is actually that every poset has a linear extension. You don't need even the finite assumption here. Yes, so we move to the other side of the building now, and we say yes, we can use axiom of choice. And there is actually some discussion. So this is a possible axiom of choice that you can take. It's weaker than the usual one. Yes, and I'm not expert in that, but anyway, we will deal here with a finite case. And in a finite case, there is a very naive algorithm that we call a generic algorithm for producing linear extension, and we'll discuss it in a moment. Yes, actually, let's discuss it just now. So, what is a generic algorithm? So when I think about linear extension, I myself actually think about this algorithm here. Yeah, and when we are building some linear extension to achieve some goal, get some property, I'm trying to think how can I specialize this algorithm to get what I want. So on an input we have an n-element poset, and then one by one we choose a minimal element in the current poset and we remove it. Yes, and that's it. And the sequence produced is a thing we can read as a linear extension. Okay, so it's pretty obvious, I think, that it gives what we want to, but let's spell it out. So the thing we are using here is actually that every finite poset has a minimal element. Even something slightly stronger, but equally obvious, that if you have a poset P, finite, and if you take an element y in a poset, should it be y? No, x. If you take an element x in the poset, then there is always a minimal element below it. Yeah? And this is pretty easy to argue if we really want to, because if this is not a minimal element, then there is an element below it. Take it. If this is not a minimal element, there is an element below it, yeah? It has to stop because the structure is finite. That's your minimal element. Okay, so this easy fact gives us that the algorithm is well defined. Yeah, because we are choosing a minimal element from something, which is presumably non-empty, yes. And now, so that is one of the 3 items I want to stress. Second is that it produces a linear extension, and if it doesn't, then there you look at the moment that you break the poset relation and you figure out that it wasn't the minimal element that you have taken. That's the way to argue. And third is that actually every linear extension is a possible outcome here. So this is like or it could be our angle of looking at the linear extensions themselves, okay? Yes, so that's the generic algorithm. Now, in this choice, there is room for specialization, yeah? So you can color your poset into red and green, and you can prefer red elements over green. And then you're claiming that your red linear extension is the best, yeah? Or something of this flavor, yes? That's something like that will happen during this lecture, and maybe we will have some exercises in this direction as well. Yes, so a first fact, important for us because we're heading for poset dimension. So take a poset and take two incomparable elements in the poset. Then there is a linear extension that puts B below A, one of your element below the other. And the other way around because this statement is symmetric, yes? Yes? How do you argue that? Well, you could argue specializing the generic algorithm. And what you want to do is you want to have B before A. So what you can do is you say that you choose A only if you have to. If there is no other option, then you choose A. And this will do. Yes? Because if you consider linear extension L that you produce, yeah, and you look at the moment that A is chosen, yeah, you look at the current poset at the moment that A is chosen. How this poset looks like? Well, A is chosen, so it's a minimal element, right, of that poset. Yeah. Possibly you have some upset. Is B around? Well, B is incomparable with A, so B cannot be in the upset. Yeah. Well, A is a minimal element, so there is no downset. So maybe B is here on the side, it sits on the side. Okay, but now then we use our very easy fact that we have argued that for every element there is a minimal element below it. Take it, let it be Z. Z is not A, because A is incomparable with B. So we have two elements, and yet we have chosen A. Something went wrong, because we elected to choose A only if there is no other option. Okay, so that proves this fact. And we have a first specialization of the generic algorithm. This has an important corollary, which has a very compact statement, yes? When you take a poset P, it's the same as you take intersection of all linear extensions of P. Now, since it's so compact, I should explain what I mean by this. So, so what do I have on this side? I mean, I'm visualizing a structure with the same ground set. Well, all P and all linear extensions, they have the same ground set. So I'm taking a structure with the same ground set. And now what is the relation that I take? It's just the intersection of all binary relations behind the L's. Yeah? And the claim is that this coincides with the poset relation that we started with. That's, why is it true? Well, we should argue the two containments, yes? So the first containment, why is it true? Well, you take a relation in the poset, so X is less than Y in the poset. Do you have it on this side? Yes, because every linear extension respects the poset. So this is correct. Take the other containment. How do we argue?
Take the pair which is not in the poset.
Yeah, maybe that's the best. So for every pair that is in the poset, it is here. Take a pair that is not in the poset. Yeah, from the thing that we just observed, it is killed in one of the linear extensions. Or if you take an incomparable pair, you always have a linear extension that does this and does this. So the relation between them disappears. Okay, very good. So if we take all linear extensions of the poset, we get the poset back. But maybe we don't have to take them all. And the minimum number that you need to take to get the poset back is the dimension. Yeah, so it's denoted by dim p, and it's the least positive integer, such that there are linear extensions that give you back the poset, such that their intersection gives the poset. So yes, let's look at some examples. our favorite poset again. I state here that it has dimension at most 2, because I'll show you 2 linear extensions of it, 2 out of these 5 that were listed before, that intersect to the poset. Yeah. To check this intersection, you'll have to go through each of the pairs, but you might have your own way to see that this is true here. So it's at most 2, and actually it's exactly 2, because dimension 1, what are posets of dimension 1? Linear, yes. As soon as you have an incomparable pair, you must have 2. Yeah, and here we have, so we actually know exactly the dimension of this poset. So now a little definitions for the further stuff. Whenever we have a set of linear extensions that intersect to the poset, we call it a realizer. Okay? Of a poset. Now this dimension sounds like something that it has some support from geometry, and there is a yes.
The realizer, need it be unique for a poset, or
excuse me, sir?
The realizer that we get for a poset, when is it unique?
No, it's not necessary. When is it unique, you say? When is it unique? Well, definitely if it's a chain, then there is only one way. But if you have an incomparable pair, when a realizer is unique?
You have 2 incomparable pairs, maybe when it's unique?
Well, it depends like how at that position, right?
When the realizer is unique. That's maybe a good exercise. When I have 2 elements that are incomparable, the realizer is unique. The optimum realizer, right? That maybe this is what we are talking about. Yes? I think it's also unique. Let's first do easy examples and get back to this question, because I'm jumping ahead of myself if I want to answer you. So just 2 slides and we get back to it. So to support this geometric intuition, let's know that we could equivalently state that dimension of a poset is the least integer d, such that you can embed elements of your poset into R to the d. In such a way that whenever you have a poset relation, then you know, between x is less than y in the poset, then the point of x is below the point of y in R to the d. And what do I mean by below? It's the, how do you call it? The product. How do you call it?
Coordinate-wise.
Yes, coordinate-wise. So please look at this example again. Yeah, there was a realizer of size 2. So now when it's of size 2, it's nice because we can draw it here on the slide. So one axis is for one linear extension, the other axis is for the other linear extension. We list the elements, and then we put them into the plane where they belong to. And then now you can observe here that, say, A is below B, and indeed the point of A is below the point of B, because on each coordinate of A is lower than for every coordinate, the coordinate of A is lower than the coordinate of B. Yes, so that's so it's I say it's equivalent. It's pretty obvious that given a realizer of size d, you can embed it into R to the d. This is the argument. The other direction is slightly. There's something slightly more to say, because if you have an embedding, it can happen that some elements have the same coordinate, and then you don't. The value is the same on some coordinate. Then you don't know how to linearize it. So you need to kind of consider kind of perturbation of this embedding. But this is easy stuff, and no one cares. So it's really equivalent angle. But most of us, definitely in combinatorics, we take the linear extension angle and take it from there. Yes. So now it's time for examples. So yes. So it was already noticed that dimension of a chain equals 1, yes? So what is the dimension of an antichain? There are lots of linear extensions here.
Number of elements.
Two, because you can take a permutation. Every permutation is a linear extension. That's fun, yeah? So you can take one permutation and you can take a reverse of it. And you kill all the relations, except the reflexivity. Yes? So we should say it's at most 2, because in the case it's a one element, it's 1, yes?
But I guess this is an example for a question about uniqueness, right? If you got
Because you fix the first one and then the other one.
if you got anti-chain of things 3, then you got more than one realizer.
Well, if it lives in some denser poset, maybe, not sure. You could have an anti-chain of size 3, but this could be put in the context, and maybe in order to get the best realizer, you have to make some choices, and there's only one way to go. What is the dimension? Okay, so since it's at most 2, let's visualize it, yes? Posets of dimension 2, you can draw them. So that's how we should look, yes? Elements that are in this quadrant are larger than this element. There are not too many of them, right? And elements of this quadrant are lower than this element, right? What is the dimension of a complete bipartite poset? Who says it? Wojciech, okay. 2. It's again at most 2, because
I don't want to be like problematic there, but why are you writing at most?
if you think about this bipartite animal, I mean, that's the rule. If you pose a question, you have to listen to the answer, right? Okay, so that's the thing, and then you should. That's the embedding, right? That's the minimal elements, and that's the maximal elements, yes? Okay. Now,
How is there, because for the previous example you said I take one linear order and the reverse one, right? How do you think about this one in terms of linear orders?
well, you can read it from here. This is L1, this is L2. So I take 1, 2, 3, 4, 5, 6, 7, 8. And then I take 1, 2, 3, 4, 5, 6, 7, 8, yes?
Yeah. Sure. Okay, thanks.
Maybe it would help if I give them the specific names and list them here.
Yeah.
One time you see it, you see it, but you have to internalize it, yeah? Okay. I'm still thinking in the background about your question. I don't know. What is the... So the dimension of this is what? It's 2, right? You see it? But it's 2. And I think there's only one way to do it.
But I meant anti-chain 3 of size 3.
Yeah, so you're saying that if you have an antichain of size 3, then you have a freedom what to do, and that there is not a unique realizer. Yeah, if this is the whole poset, true. But if it's put in the context, I don't know. And I don't have a concise answer. This is recorded, unfortunately. So, so let's keep it in the background. We will solve it. Tom will give you an answer before the end of this lecture. Okay. So this is exactly 2 years. Let's move on. Yeah. So that was my drawings for the slides. So these green posets here at the right bottom, these are like some examples of posets of dimension 3. There is a complete list of it. There are of minimal posets of dimension 3. It's not a finite list, but there is it is listed, yes. And there is a good understanding of it. It's non-trivial to give the whole list. Yeah, it takes an argument. So this one we call spider, and this one is a chevron. Yeah. Yes. So you see, we can draw dimension 2. And actually, we have a pretty good understanding what are posets of dimension 2, and you have seen them in combinatorics, just under different names. So this should be a comfort zone for all of us. And as such, we're not going to discuss it here. So these statements are equivalent, but perhaps we do it as an exercise. So 1, G is a comparability graph of a poset of dimension most 2. Coincides with that G is a containment graph of intervals on a line. Yeah, what do I mean by containment graph of intervals on a line? Well, vertices of my graph are intervals. There is a line, yes? And vertices of my graph are intervals. And 2 vertices are adjacent if one interval is contained in the other. Yeah? So this way you can have some complex structures perhaps, but it happens that this class of graphs is exactly the class of comparability graphs of posets of dimension most 2. Furthermore, it coincides with the so-called permutation graphs. Now everyone has a favorite definition of a permutation graph. I like to look at them as intersection graph of segments spanned between 2 lines. Yeah? So vertices are segments, and 2 vertices are adjacent if the segments intersect. There is a reason why it's called permutation graph, and it's there. The fourth one is something you maybe haven't seen, and it will be useful just in the next line. So it says that, well, G and the complement of G, both are comparability graphs. Yeah, so let's flip it back. So let's start from a poset. Yeah. Now, from this poset, look at its comparability graph. Yeah. So what is the condition that a graph is a comparability graph? It means that you can orient the edges such that the orientation is transitive, and it's acyclic. Sorry. Yeah, I should add. Yeah, that's the So when you have a graph such that you can orient it, and you take a complement, and you can again orient it to make it transitive and acyclic, then the poset behind it is 2-dimensional. This gives you a way to test if dimension is of most 2, because it's a pretty classic setup to given a graph to verify if it has a transitive orientation. This can be done in polynomial time. Do you know exactly the time? I used to know, but I don't have it from top of my head. But if you look at the dimension 3, it gets hard immediately. And this is a thing we used to see as this step from 2 to 3 in coloring or anything. It's an NP hard problem. For any given k greater than 3, if a poset has dimension most k, it's an NP hard problem. This was the reduction goes from free colorability, and it's done by Yanakakis, one of the earliest NP hardness results ever, 1982. Before this problem, if it's NP hard or not, was listed in this famous at the time Gary Johnson list of computational problems to be investigated. Okay, that's a nice narrative, but you should say hello. Okay, I take it it's NP hard to say if poset has dimension most 3, but maybe all posets have dimension most 10. Not totally excluded yet, but it's not true. And if there is justice in the world, then Boolean lattice of order n should have dimension n. And it does. Yeah, so we look at the poset, one of the most standard posets ever, yeah, poset induced by all the subsets of an element set. Yeah. And yes, we want to see, we are rather interested in the lower bound here, but just to mention that that there is an argument for an upper bound here, and it's easily seen by specialization of the generic algorithm. So what do you need to do? You need to construct a realizer for Bn. Imagine that your elements, the elements of the posets, are a subset of 1 to n. Yeah? So every element x in Bn is actually a subset of 1 to n. Yeah? That's the names of my ground set. And now I want to produce a realizer of size n. So what is Li? Well, I produce it by the generic algorithm, and over there I prefer elements that do not have element I. Yeah? So I'm trying to read this poset, take a linear extension, but every time I have a chance to take an element that does not contain I do it. And there you can see that it's a realizer. Yeah, that every incomparable pair is reversed. Perhaps we do it in the exercise session. But the lower bound is the thing we need here. Some argument that there is something, that drives dimension up, and there is something. We call it standard example. Where can you find it? Well, look at your lattice again. Yeah, there is an empty set at the bottom. There is a complete set at the top. But look at the singletons. Yeah, B5, so 5 of them. Look at the co-singletons, also 5 of them. What is the poset relation between them? The poset relation is containment of the sets, yeah? So the set singleton 3 is below all the co-singletons except the one corresponding to 3 itself, because, yeah? And the same star you can see from the co-singleton above. So this is the poset relation, yeah? When you take the 5 elements at the bottom and 5 elements at the top, it's a complete bipartite poset, but a matching. So that's a standard example of order 5, and in general, a standard example of order n is a poset on 2n elements, where the minimal elements, let's call them A1, AN, the maximal elements B1, Bn. And now AI is less than Bj if and only if I and j are distinct, or different. Yeah? And here you have a picture of the smallest reasonable standard example of size 2, and size 3 next to it.
And you miss an edge? Yeah.
Oh, come on. Do I miss some? Yes, I miss this edge. Only this one or something? Yes. Thanks, good spot. So, yes. Okay, so you can find a standard example of order n in a Boolean lattice of order n. The claim is that the standard examples drive dimension up. Actually, the upper bound you have already seen because we mentioned how to do it for the whole Boolean lattice. The lower bound still is the thing. But this, now I really give you the argument.
For the Boolean lattice, wouldn't it be simpler to just directly embed it in R2the n by just saying that on the if coordinate I put a 0 or 1 depending whether the element is inside or not?
Yes. It's a matter of taste, Michal, I guess, but yes, sure. Then you kind of use the thing that you can use the same value on coordinates, yeah, and this makes it handy in this, yeah. Yes, so we want to prove that dimension of Sn is at least n. How do we argue? Well, consider a realizer. L1 up to LD, yeah, of Sn. And what do we want to argue here? We want to argue that this realizer is large. So we want to argue that D is at least n. Okay? realizer reverses incomparable pairs. There are not too many of incomparable pairs in the picture. Well, at the bottom you have lots of incomparable ones at the top, but there are some pairs that look distinct. Yeah? These are the pairs of the matching. And then it should be, it feels like it should be more difficult to put B below A. And there must be a linear extension to put BI below AI, if it's a realizer. So let's look at it. And so fix I in 1 to n. And since this is a realizer, there exists J in 1 to D, such that BI is less than AI in LJ. Yes? Okay, that's a pretty strong requirement. How does the LJ look like? So it has BI, yeah. It has AI somewhere above. Where are the other A's? All the other A's are in the poset below BI. And since this is a linear extension, yeah, this is a linear extension of Sn, it must respect it. So all the other A's are here, yeah? This is A minus AI. Well, by AI, I mean all the A1 to AN, maybe all the maximals. And also all the B's, all the other B's, but BI must be here, because they are all above AI. So here is B minus BI. So for this fixed value of I, we have chosen J, and let's call it like some function of I. And then the thing to observe is that for distinct values of I, we have to fix distinct values here. Because if you elect to reverse AIPI, you cannot reverse anything else of this type. So the claim is, which was proven that if I is distinct than J, then phi is distinct than phi J. Yeah, but since there are n values to fix, we need this set to be to accommodate that, yeah, which proves this inequality. So there are posets of large dimension. Yes, and as such we have exactly the dimension of the Boolean lattice to be n. So please note that already within this we see that dimension can be arbitrarily large already on height 2 posets, which looks quite innocent, but yet complex with our measure. How about the width? How about the width? So Dilworth already observed it, that dimension is bounded by the width. How to argue that? Well, 1950, it coincides with, it's the same paper, right? It coincides with the Dilworth chain partition. So what you do, you have the width W of a poset, take the chain partition of poset into W chains, and now construct a set of linear extensions, one for each chain. How do you do it? Well, specialize the generic algorithm. When you want to produce Li, elect to prefer all other elements before elements in Ci. And that will do. That will do. Why is it so? Well, so the claim is that L1 up to L, what is the index? W is a realizer of P. So how do we prove that something is a realizer of P? Well, we need to take an incomparable pair. So X, Y in the incomparable pairs. Inc of P is the set of incomparable pairs of the poset P. And we need to show that there is a linear extension here that puts Y before X. That's all we need to do. So X, Y are incomparable in P. This means that they have to be in different chains of the chain partition. You agree? So X is in Ci, Y is in Cj, and I is distinct from J. Okay. Now we are looking for a linear extension that puts Y before X. X should be late, X is in Ci, so we want to look at Li. Let's look at Li. Let's consider the moment that X is chosen. How does it look like? Well, what is the poset? Well, X is definitely a minimal element because it's chosen. Perhaps there is some upset. There is no downset. Yeah? Ci is an orange chain. X is orange. Maybe there are some other orange elements here. Nothing below because X is minimal. Y. Y is incomparable with X, so Y is not here. Yeah? We want to argue that Y is already taken. So suppose not. So suppose Y lives here. From our basic fact, there is a minimal element hanging below Y. Let's call it Z. Critical observation, Z is not orange. Well, because X and Z are minimal at the time, and X is orange, and orange is a chain. Okay, so why didn't we choose X, Z? That proves the fact. So, large dimensional posets are wide, but not necessarily tall. And now it's the moment that we start to look at the zoo. Okay? Well, there are some animals. There was a box for standard examples. It's already driven away. There are some other nice examples. And all this lecture here, the first of the five, is actually to give you some examples that show up, that are important, that kind of set up all the scene for research. Okay, and so there are these two ways to make a poset from a graph. One is here, incidence posets. So given a graph G, you can construct a poset. So the elements of it are the vertices and the edges of your graph, yeah? And then it basically looks like that you have vertices are your minimal elements, yeah? And whenever there is an edge between two vertices, there is an edge E, yeah? That is, this element in the poset is above exactly these two elements corresponding to the vertices. And this is an incidence poset of an initial graph G. Now, well, you see, so if you have a clique of size 4, yeah, then the poset you have has 4 minimal elements and 4 choose 2 maximal elements corresponding to edges, right? And the fact is that if you take larger and larger cliques, the dimension goes up. It grows like log n. This is actually right asymptotics. But again, I want to show you the lower bound because the way to argue the dimension is large is important. Ideas how to argue the dimension is large are important for this. Why do I make a big deal out of this example? One reason is that there are no large standard examples here. So this already sets up some important things. So dimension is monotone, yes. So dimension of Q is less or equal than dimension of P if Q is a subposet of P. When I take a subposet, I always think induced. So there is an obvious monotonicity. So, like with graphs, yeah? If you have a large clique, then you have a large chromatic number. But do you need a large clique to get a large chromatic number? Yeah, do you need large standard examples to get dimension large? Also not, because this is one of the critical examples here, yes? These elements at the top have degree 2. So you can have S3, right? I think you can, yes? Because S3 would be just IK3 is A3. It gives you S3, right? If I'm not mistaken, yes. Yeah. This is another S3. But you don't have larger standard examples. So if you define a standard example number to be the largest size of the standard example in the poset, and it's 1 if there is no standard example, then the standard example number of this is 3, yet dimension unbounded. Interesting. Proof. How do we argue? We need a different argument. Yeah?
So which one are you arguing? The no standard examples or the...
Oh, I just finished the argument for no standard examples. So
log n, that's what you're arguing?
Yes, yes. So Shimon, look, if you have IG, yeah, then how do the vertices here at the top look like? They have degree 2, yeah. So how can you find your standard examples? Well, the bottom elements are here, top elements are here, but you know, if you have Sn, you must have degree n-1, yes. So there is simply no way, yeah. So that's why it's at most 3. Yes, but the proof will be for the dimension now. Dimension of IKN is large, gross, yeah. How do we argue? So yeah, so we need to argue that the dimension is large, so we should take a realizer. So take a linear extension, L1 up to LD, a realizer of, what is the poset? IKN. And we want it again, is that D is omega log n, yes? This will complete the proof. IKN. Vertices, edges. And elements, and choose 2 elements. Linear extensions of this. When you look at a linear extension, let vertices be orange, okay? Consider how the orange vertices are listed in L1, yeah? And how they are listed in L2. Well, orange is an antichain, so it's an arbitrary permutation. But if it's large enough, we can find a subsequence that behaves the same up to dual, taking dual, yes? And that's Erdős-Szökeres. So by Erdős-Szökeres, there is so let's so V1 is the vertex set of Kn, yeah. There is V2, a subset of V1. The size of V2 is at least square root of n, such that the order of orange is this in L1 and L2 is the same up to taking dual.
You mean reversal?
Yes. So either it's like, you know, A, B, C, D, and then it's the same here, or D, C, B, A, yes? Something like that. I managed to... I shouldn't explain anything here, I think. Yes. So now we iterate. We have D linear extensions. So we iterate. Yeah, we take the subset V2 and we confront it with L3, and we get V3, and we iterate. So at the very end, there exists VD, yeah, which is a subset of the original one, and now the size of VD. So every time we take a square root. So it's at least n to the D minus 1. This is the size. And then what is the property? It's such that the order of vertices in BD, orange in B2, yes? Of vertices in BD in L1, L2, up to LD is the same up to reversing. So we claim to have a realizer, yet we can find a set which behaves basically the same everywhere. If the set is large, we have a problem, and large means 3 elements. So if VD is of size at least 3, then consider 3 elements A, B, C in VD. Yeah, so you have, that's how it looks in the poset. How does it look in the linear extensions? So in L1, say you have A, B, C. 3 letters this should be. In another you have A, B, C. Somewhere else C, B, A. A, B, C. C, B, A, yeah? That's how it goes. This is L1, L2, L3. Where's the problem? B is in the middle. How to exploit it?
The click is...
That's an edge AC. It's an element of a poset. Where is it in L1? Linear extension. L1 is a linear extension. It has to respect the poset. So AC has to be above elements that is above in the poset. It has to be above A and above C. So it's somewhere here. Where is it in L2? Here. In L3, C, A. Here. Everywhere it's about the 3 elements. Why is it a problem? B and AC is an incomparable pair in RKN, yeah? And this thing claimed to be a realizer, which means that there should be a linear extension that put AC below B. But there is not. So that's a contradiction with this assumption that VD is of size at most 3, and this will give us a bound, right? Because now we know that VD is of size at most 2. On the other hand, we have a lower bound on it, which is n to the 1 to the 2 to 2 to the d minus 1. So if we take a logarithm, we have 1 over 2 to the d minus 1 log n which means that this is log n. I'm terribly slow, sorry. 2 to the d minus 1. So this means that log n plus 1 is less than d. As desired. So this omega could be replaced by a nice looking function.
That's the lower bound. Right? And for the upper?
Yes, this is the right asymptotics. You can argue it's not terribly difficult. Maybe we do it in this exercise session. It doesn't fit to my narrative, so I skipped that here. But it's the answer. Again, I wanted to show you how to argue that dimension is large, and that's a truly different argument than the one from before, right? For the standard examples.
Although, just want to make a quick comment, you can now write down the answer for this problem almost surely exactly. You never miss it by more than 1.
Additive constant, yeah?
No. You never miss it by more than 1, and almost surely you write down the right answer.
Oh, I see. So there is some probabilistic stuff behind.
It doesn't fit your theme at all.
Clearly. Yes. There was, maybe there is some deep research behind it, going back to 80s, I think, and this number is well understood here. And these incidence posets, well, they show up. Yeah, this is far beyond posets and its dimension themselves, their dimension. Yes. So another animal, interval orders. That's a cute one. So given a family of intervals, you can build a poset on top of it, yeah, with a pretty obvious way. So one interval is less than the other if it's completely left of it, yes, disjoint and completely left. And then so here's some visualization. You see, you have A and B. So elements of your posets are now intervals, yeah, and two intervals are. Two elements are incomparable if the intervals intersect. Yeah? And if they don't intersect, there is a clear relation. One is less than the other. Now I want to have a canonical thing to tell you that dimension goes up. So this is what we call a universal interval order. And you basically, you take, you consider all the natural coordinates from 1 to n, and you take all intervals in endpoints within these coordinates, and that's the poset, yeah. And fact is that dimension goes up again, like log n. Again, this is the right asymptotics. This is even more interesting in terms of from the standard example angle, because actually it is relatively easy, but maybe not completely trivial to prove that if you consider posets that do not have S2, then this class, that's a class of posets, yeah? This class is not trivial actually, and it exactly coincides with interval orders. Yeah? So there are two implications to prove here. One is easy. It's easy to given that you have an interval representation, it's easy to see that you are unable to find 2 plus S2 over there. The other direction is where you need a little argument, inductive usually, to proceed, but it's true. What does it say? Well, it says that actually, you have no standard examples at all. So the standard example number would be 1 if you define it properly. Yet dimension arbitrarily large. Now, how do we argue? Well, we need to get sidetracked for a moment and do some fun. So here is the ship graph. You have a graph. The vertices are pairs again. Pairs of integers from 1 to n, yeah? Order it. So always the first coordinate is less than the second, like an interval. You should visualize intervals here. And when do we have an edge now in our graph? When do we have an edge in the ship graph? Well, it is it is when so this is I, this is J. You have an object like this. So it is adjacent. It's not adjacent with this. It's not adjacent with this. It's adjacent with all the objects that left endpoint coincides with our right endpoint, and also with all the objects that right endpoint coincides with our left endpoint. That's the adjacencies of my favorite IJ. Okay? And that's a graph. It's there are jokes like how much in the kindergarten you have to be in Hungary to actually know this proof. Who knows the proof for this inequality? Huh? Someone should raise a hand here. Okay, 2 of you. Okay, let's do it then. Let's do it. Because we are not yet there, it seems. And it's fun. Blackboard, okay. Can I prove it? Yes, I can. So chi of Gn is actually, this is the right number, by the way. Exactly, this is the ceiling of log n. And there is an easy way to color it. You know, divide and conquer, very easy stuff. You can defend log n. That's the easy part. This is nice because if you give it to someone that didn't see it, it's not entirely trivial where to go. That's why, and when you see it, it feels very easy. So let's go. So what do we do? Lower bound. So I should fix a coloring. So let's fix phi to be a vertex coloring of Gn, and assume that I'm using k colors. So what do I want? I want that k is, at least log n, yes? So since it's an integer, it's at least the ceiling of log n. So I fix a coloring, proper coloring. Now, there are these coordinates, yeah, from 1 to n. Look at coordinate I, yeah, and there are these pairs. So I from the interval orders, I look at them as intervals, yeah, that end here, yeah, and they have colors, right? Because everything is colored here. So maybe this is orange, yeah, and this is blue, and so on, yeah. And now I want to collect these colors here. So xi is a collection of colors that I see. So it's a phi of what? AI for all a less than I greater or equal 1. Yes? It's the collection of colors that I see. And the claim should be definitely that when I is distinct from j, then we have xi distinct from xj. Distinct. I mean distinct.
Oh, sorry. That's not the definition.
No, it's a pleasure. I and j, yes? So we have two sets. One colors are here, the other colors are here. we claim that the two sets are distinct because there is this guy that is maybe green, and green belongs to xj. Can it be an xi? No, because then the coloring wouldn't be legal. So this proves the claim, and since we have n sets, and how many possible this is a subset of colors, so we have 2 to the k possible evaluations, and this should be enough for n coordinates. So we have this inequality, which proves that k is greater than log n. Okay, that was one fun fact. Now, there is a double shift graph. In general, you can have a generalized shift graphs here, and it's equally fun. So in the double setup that we need to take to get to universal interval orders, vertices are triples, not pairs but triples, ordered ijk, I less than j than k. All of them are integers between 1 and n. Yeah, that's the vertices of Gn3. And the edge is when one triple kind of agrees with the other triple, yeah? So the suffix of one of size 2 coincides with the prefix of the other of size 2. Yeah? So the picture should be that this is one triple, ijk, and it's adjacent, for example, with this triple, jkl. Yes? That's the graph. And now it happens that this graph also has chromatic number that grows if our ground set grows, and it grows like log n. I know what's coming next, so I'm going to go. So chi Gn3 is at least log n. How do you prove it? Fix a coloring. Proper coloring. And now you want to fix 2 coordinates, and you want to look at set xij, which are all the colors that you see on triples that end here in I and j. Yeah? Collect all the colors. So this is a set of phi a I j such that 1 less than I, well, less or equal a less than I less than j less or equal n. What is the claim now? Claim is that this is a proper coloring of the shift graph. So if you consider sending a pair ij to its subset xij, then it's a proper coloring of Gn, the usual. Now I can put number 2 indicating that I'm talking about pairs. Yeah, that was the original shift graph. Why does it hold? So yeah, maybe it's a little bit abstract. Yeah, what did happen here? I fixed these 2 integers. I consider some subset of colors from my coloring. Yeah, so now I can consider this to be a coloring of this, a color of this pair. And now I claim that this is a proper coloring of this Gn2 that is a graph on the pairs. Yes. So in order to see that it's proper, I need to consider 2 adjacent vertices in Gn2. Yes. So two adjacent vertices in GN2. This is I, J, and K. Yeah, that's one vertex, and that's the other vertex, and they are adjacent. So now we claim that xij has to be different than xjk. And it is, yes? It is. Because this beautiful orange vertex, orange, belongs to xjk. Can it belong to xij? If it did, you would have someone witnessing it, and then this orange with this orange would kill the fact that the coloring was proper that we started with. This proves it. So the claim. So this means that. What does it mean? It means that. How many colors am I using? I started from k colors and I generated 2 to the k. So my coloring of GN2 used at most 2 to the k colors, and I know that the chromatic number, so this should be greater than the chromatic number of GN2, right? Which we already have seen is at least log n, which completes the proof, yes? Because this implies that k is greater than log n. Okay, very good. That's enough fun. So, yeah, we are back to the poset zoo, and we want to argue that dimension of the universal interval order grows. How do we do it? Imagine what? I have it on slides. So we, how we should argue? Well, dimension is large, so you should take a realizer, and you should argue that it's large. So consider your favorite realizer, and we will argue that D is at least log n. How do we do it? Well, we use this realizer to color GN3. So given a triple ijk, what do we do? Well, first of all, we are talking about poset UN. So our objects there are intervals, yeah? So there is an interval ij, there is an interval jk. Now I should mention, I guess before, that I consider closed intervals. I find it convenient that ij is incomparable with jk. Universal order on open intervals also have this dimension growing and nothing is changing, but it's convenient for us here to have these two intervals incomparable. Because if they're incomparable and we have a realizer, someone has to reverse them. That will be the color of ijk. So choose alpha, yeah, such that jk is less than ij in L alpha. Yeah, let it be phi of ijk. Claim, that's the proper coloring of GN3. Proof? Okay. What should be the proof of the claim? So assume that phi ijk is equal alpha, which is equal phi of jkl. And we want to get a contradiction. That's two vertices of GN3 that are adjacent. We want to find a contradiction. So let's do it. 4 coordinates, I, j, k, l. What does it mean that this is alpha? This is alpha. This means that jk is less than ij in L alpha. Yes? But what does it mean that this is alpha? This means that kl is less than jk in L alpha. KL is less than JK in L alpha. Do you see a problem? Yeah, this guy is missing. So orange guy in the poset is below the blue guy. Yeah, definitely. Yet this is blue and this is orange, and we are in a linear extension. And that's a contradiction with the assumption that the coloring is not proper, so it's proper. Since it's proper, we have a bound because we use D colors, where D was the size of our realizer. So, so indeed, a realizer of this universal interval order has to be large, as claimed. Okay. And now the last for today animal in the zoo, another operator that, given a graph, gives us back a poset. This will be called an adjacency poset of a graph. So this time, given n vertices, for each vertex of your graph, you will produce an incomparable pair. So V gives you AV, BV. This will be incomparable pair in the final poset. And whenever you have an edge, UV in the graph, one pair with the other interacts in this way. So A is below the B, and the other A is below the other B. Okay? And that's it. Now, what could we observe here? Well, one thing to observe is that this is a kind of method, a very brutal method to given a complex situation on the graph side, like a triangle-free graph with a large chromatic number, will give us a complex thing on the poset side. Yeah? So the thing to observe is that if G is triangle-free, whenever you have an edge, you have a standard example of size 2. But it works the other way around. So if you would have a standard example of size K, you would need to have a click in the initial graph. Therefore, when G is triangle-free, the standard example number of your poset is at most 2. So that's indeed a way to produce something that avoids standard examples. So given the fact that I'm about to tell you that dimension can be lower bounded, gives us another animal in the family. By the way, this is the only way that I know to produce a poset of large dimension such that its cover graph has large curve. I don't know how to do it any other way. Do you know, Tom? So, yeah. So let's prove this. The statement is that that dimension is at least a chromatic number. Dimension of AG is at least a chromatic number of G. So, dimension is most a chromatic number. So we should take a realizer and produce a coloring of graph. So take a realizer, L1, LD of AG. Okay, AG is a fun poset. Given the vertex V in VG, you have AV, BV, which are incomparable. Since this is a realizer, someone reverses this pair. Its index will be the color. So fix V in VG, choose alpha from 1 to D, such that BV is less than AV in L alpha. Yeah, and let it be let it be that we fix phi of v to be alpha. And now the claim is that phi is a proper coloring of G. In order to see it, you need to take two vertices u and v, adjacent, and you need to argue that they have different colors. So assume that this guy has color alpha. It has color alpha. What does it mean? It means that BV is less than AV in L alpha, yes? Yeah, what is the poset? So U adjacent with V, V, this is U, AU, BU, and we have this. This is what happens in a linear extension of my poset. Here's AV. BU is above AV in the poset, so it has to be in a linear extension. And AU is below BV in the poset, so it has to be in a linear extension, which means that U, AU, and BU is not reversed in L alpha. So the color of U is different than alpha, which proves the claim. And since the number of colors we use is what we want to, so we have proven that D upper bounds the chromatic number of the graph. And when we take the optimal realizer, we prove the inequality. I hope to see some of you tomorrow. Thank you.